Well, as we heard, so I started my life studying astrophysics, and then I did a PhD, and it kind of took hold of me in enough that I actually decided to carry on in academia, and I did about 10 years of professional research in astronomy. I was in London at UCL, and then I ended up moving out to the European Southern Observatory in Germany, in Munich, and I did a postdoc there. And you know, to observe the whole sky, you need telescopes everywhere. So the European Southern Observatory was the place that ran the telescopes for the European countries in Chile. Maybe some of you have been. I mean, so it's a spectacular place to go and visit. And yeah, that is, you know, right up in the mountain, in the middle of nowhere, in the desert. It's like the most amazing place. So we got to go occasionally down to Chile and you know, look at the telescope, use the telescopes and things. But then after a little bit of time, I should say, should start here. 2008, maybe you can't quite see the number, but that was me back in my astronomy days when I was quite a bit younger. This is on Mauna Kea in Hawaii. This is the Subaru telescope, which is what we had a couple of nights on there. Yeah, it sounds very exciting and, you know, yeah, it gets you around the world, all sorts of things. But I know in the end, I decided that astronomy as a professional career wasn't really what I wanted to do. And I, it was about a year of considering, and then I decided I was going to finish after the postdoc. And I moved back to London. I had already been teaching a bit of yoga. And so I thought, well, let's give that a go. So I started to teach yoga. And quite quickly after then, I started to teach meditation. And it was a little bit, yeah, people keep telling me, Mark, you need to find a way of bringing the meditation and the yoga and the astronomy together. And I couldn't work it out. I just couldn't see a connection. I thought the astronomy was just receding in the rearview mirror, you know, and I just was this new life. And then my wife got a job, 2 years contract, working on the island of St. Helena. You come in, please. Yeah, come in, yeah. Yeah, there's a couple of seats here. No, please, come on. Yeah, come through, yeah. So my wife got a job on the island of St. Helena. St. Helena, I don't know if you're aware of, it's a tiny, tiny little speck of an island in the South Atlantic. You're nodding. Yeah, not too many people know where it was. We didn't know where it was. She just got this job out of the blue. She's a speech and language therapist, which is not too, you know, wouldn't think you'd go around the world doing that. But anyway, St. Helena is a British island, British overseas island, and we went down there for 2 years. And it's the kind of place where there's zero light pollution. There was a little astronomy club, and there's been a little bit things going on over the years. So I got a little bit involved, and up on the hill, we had a house where we were living, and you could walk out the back door, sit on the chair, and it'd be the most spectacularly dark night, you know, from horizon to horizon. And of course, it's just into the southern hemisphere, which means you get to see some of the southern stars, Southern Cross, Magellanic Clouds. And it was the most magical time. She was working, I wasn't working. So I just swung on a hammock most days and enjoyed the night sky. And it totally rekindled my passion for this kind of stuff. Yeah, so when we came back from St. Helena, I'd written, these days I kind of lead, you know, astronomy stuff, and I've written a few books over the years. As we mentioned, I've got a couple with me. This one here is an adult book around combining meditation and contemplation, awareness, contemplating our place in the universe, really, with the astronomy and science. There's even a couple of equations somewhere buried in that one. And then this one just came out in February. This is a kid's book for like primary school age, really all about exciting that kind of curiosity about the universe and what it means to live in the universe and how we can, you know, open the curtains at bedtime and look out and see what you see. Yeah, so if anyone has got any kids in mind that they know primary school age, it's a one to look at. Now, let's see. what I wanted to tell you a story today, and the story is the history of our universe. So we live in a very unusual time in that it's only been the last, I don't know, a couple of generations that we've known the story of the universe. If you go back, let's say even 100 years, we didn't even know that Milky Way, that there was anything outside the Milky Way, right? 1929. People thought that there was these island universes, didn't know that there was anything outside the Milky Way. So, and then now we know that the universe is expanding. The universe is expanding because it started in a Big Bang. So the whole idea of the Big Bang was from the 1950s, and it wasn't until the 1960s that we had any kind of evidence for the fact that there was a Big Bang. We know the history of our planet. We know the age of our planet, which again came in the older 50s or 60s, measurement of the age of our planet, age of our solar system. So it's really just been the last, and that information started off as very academic, and only academics would know about it. And it gradually filtered its way down, and to now, if you probably speak to most people just on the street, they'd have some vague idea that there was a Big Bang, that the universe is very old, and you know the stars are very, very far away, and the star is a big ball of gas, something like that. Most people get taught, right? So that kind of knowledge wasn't even available 100 years ago at least, yeah. So very, very unusual, unprecedented time that most people have an idea of the history of our universe. And of course, that history is our history. It is our story because we are made of the universe. We are the universe, yeah? The stuff that we're made from is not separate from, we don't exist separate from looking at the universe. We are in the universe, made of the universe, exploring the universe. So this is the area of what I would call mindful stargazing, which is like, there's an element of actually being out in the night sky and looking up and immersing yourself in the experience of being with the stars. Last night I was with a group down in Crowborough in Sussex, and we were just saying before we started, we had the most beautiful clear night. The weather, the forecast was for cloudy, but it actually turned out to be beautiful. Had a group in the middle of the field and just lying down doing things that people just don't do these days. Lying down, looking at the stars, isn't it? Yeah. So there's an element of being in the nighttime and looking at the stars, but there's also an element in this mindful approach of contemplating our relationship to the universe and what it means to be a human living in this kind of space, right, in this time. Yeah. So I'm going to tell the story in terms of the periodic table. Maybe it's familiar or maybe it's vaguely familiar. Okay, so this is all the elements that we know about, arranged in terms of the weight, the atomic number, so how many protons and electrons there are. And we start off with the most simplest up at the top left there, hydrogen. Hydrogen is one proton and one electron. Now, when the universe began, so physics, now we understand, right? It's probably only the last, I don't know, 30, 40, maybe 40, 50 years that we've understood this. But the universe began 13.8 billion years ago with this enormous explosion. So the entirety of the universe was condensed into a single point. Absolutely mind-boggling. You cannot even imagine what that would have been like. A single point where the entire universe was in. Now, it's extremely energetic, so anything with a lot of heat expands very quickly. So it expanded quickly. It was like an explosion, really. And out of this pure energy, material was able to solidify. So we get the first particles solidifying out of this pure energy. Electrons, quarks, those kind of things. Quarks came together to form what we know as protons and neutrons and various other particles. Now, one proton is hydrogen. And then later, as things cooled a little bit more, it was able to attract an electron and becomes neutral hydrogen. Yeah. So the universe produced all the hydrogen that we know about in the first 3 minutes after the Big Bang. Enormous amounts of protons. And they're just floating around in space 13.8 billion years. Like there's another number that's just absolutely inconceivable, right? So even when, when I was working in astronomy, we'd take these big numbers and make them smaller because it was easier to comprehend. 13.8 billion, so a billion is 10 to the 9, so we call it 13.8 10 to the 9, which is kind of slightly easier than going 13.8 thousand million years. Wow, and all these O's, zeros afterwards, yeah. So 1 billion years is a 1,000 million years. 1,000 million years. So all this hydrogen produced at the beginning of the universe, very, very hot, and then was floating around and came together in big clouds. And of course, nothing is uniform in the universe, so we get these clumps, slightly more dense, slightly less dense. And over time, gravity pulls the clumps together and they get more and more dense and then start to heat up, and the pressure starts to build as more material flows in, more and more hydrogen, until you get a ball of hydrogen, hot enough and dense enough for nuclear fusion to start. And there's the first star. So a star, a ball of hydrogen with a nuclear fusion, which is converting hydrogen into helium. So that's the next one up here. So it's squishing two protons together to form helium, which is two protons, yeah? Now, just to give you a little sense of how complicated and how long it took for people to work this all out. Yeah, it's just been the last 100 years, and quite a lot of has had to come into place to us to figure this out. There are two main ways in which stars squish together protons to form helium, squish together hydrogen to form helium. One is the PP chain, which has a series of reactions. So you start off with hydrogen over that side and helium over this side. And then the other is the triple alpha process, where it involves some heavier elements which decay, and then you end up with helium. So different sort of processes. We don't have to worry about the details. Yeah. There's a sort of potted history. Now, I hate slides with loads and loads of text on, but here we are with one of those. And I just wanted to give you, I wanted to put it like this in order to show you just how much there's been going, and this is just the highlights, right? So we start off in the 1920s with Arthur Eddington proposing that stars shine because they're converting hydrogen into helium. So prior to that, these stars, how are they shining? Where's the energy coming from? So this is an idea that Eddington had, 1920s. And then it took a few years of some discoveries in the lab to try to figure out some of the particles. So only 1932 they discovered the neutron. The neutron is really important in this process. So you need to know that there was a neutron even. And then 1938 they proposed this PP chain, simplest way for stars to turn hydrogen into helium. And then some various other bits and pieces, so other cycles. And then in the 50s, people had the idea, okay, so stars are not just converting hydrogen to helium. Actually, there are more elements that are being created here along the line, right? So if we then go back. So the universe produced almost all exclusively hydrogen, tiny bits of other things. But then as we carry on going there, we've got lithium, beryllium, boron, carbon, nitrogen, oxygen, as we get further along the periodic table, as the elements become heavier and more protons, basically, and then a few neutrons. So then there's this idea that here, 1950s, people realized that stars could actually squish together helium and produce some of the next heavier elements: boron, carbon, nitrogen, oxygen. In the 1952 here, we've got the idea that helium can fuse into carbon. Of course, we are mostly made of carbon. In fact, our life is based on carbon. So people had this question, well, where did all the carbon come from? If stars are converting hydrogen into helium, where does the carbon come from? There has to be a way that stars can produce quite a lot of carbon so that we can actually live. Yeah. Then 1955, the idea that stars are born of different sizes. So they call this the initial mass function. So basically the relationship which describes how many small stars, how many medium stars, and how many big stars are made inside a gas cloud. So you need to know what is the distribution of sizes of stars in order to understand what the different stars are doing and how they're contributing towards the build-up of material. And then here, this is a very important paper, 1957. Burbage, Fowler and Hoyle can present a complete synthesis of the nuclear synthesis processes solidifying the modern framework. Okay, so they've taken all this stuff that's been going on before, stuff that's been going on in the lab, stuff that's been going on in theory, stuff that's been going on in the discoveries in space, and came up with a kind of picture of how this stuff works, all the equations, all the atomic physics and all that kind of stuff. Now we start to get a little bit more complicated as people start to realize, okay, the physics of how this works is really hard. How smaller, lighter elements end up being heavier. And then here we've got the lifetimes of stars. Now small stars last a very long time, and big stars shine for a very short time in the cosmic scheme of things, right? Low mass stars like our sun is a medium to small star, right? It's been shining for about 5 billion years, and it's got about 5 billion years left. Whereas a star maybe 10 times the size of our sun lives for about 50 million years. A blink of an eye compared to the star like our sun. Yeah, so we have to understand that different stars have different lifestyles. Well, I mean, I don't know, you know, they're all kind of shining. Life cycles, they live different lengths of time. And then also what happens in a supernova is also really important as well to understand this. So a supernova is the end of a very massive star, and the energies involved in this explosion cause even heavier elements to form, and we'll explore that a bit in a minute. Yeah.
And I believe red dwarfs, they last for a titanic period of time, don't they?
Yeah, that's right. Yeah, that's right. So stars that are even smaller than our sun, yeah, like red dwarfs or brown, what do they call them? Brown dwarfs. Yeah. So almost stars to small stars, they will last pretty much the entire history of the universe. Yeah. And then they're just fizzling very slowly. Yeah, so just to give you a sort of sense of the background of physics that's had to happen over the last, and it starts off in the 1920s. What are we now? 2026. So it's 100 years of knowledge that we built up. And I would argue that if you were to say this to someone in 1850, they wouldn't know what to do. They wouldn't believe you. You know, they wouldn't even comprehend that this was even possible. They might even get locked up in an asylum for talking about this kind of stuff, you know. Yeah, it depends who you talk to, right? Yeah. Hopefully this is a friendly audience. I'm not going to get locked up after this. Yeah. Right, so this is some background. Now let's try and make it a bit more connected to reality. Now, what are we looking at here? Anyone have any ideas?
Dark gas cloud.
There's a dark gas cloud. Yep. There's something happening up here. Yep, that's right. Yeah, I've forgotten my laser today, sorry. Yep.
It's not the top of that pillar of creation.
It is not the pillar of creation, but is a pillar, yeah. One of these pillars, yeah. So this is a big dark gas cloud, and there in the top there's a star in the foreground, so it's bright, but all these other stars are in the background. You can see they're being obscured by this big cloud here, fading out. Now this is an image taken in visible light, but we can also look at this in lots of different parts of the electromagnetic spectrum. So here there's an image taken, here we are, yeah. This is with radio waves, looking at the CO molecule, carbon monoxide. And now we say, oh gosh, there's something really happening inside the cloud. Now, in the radio waves, the cloud is invisible, it's transparent to radio waves. So we can see right in and see this hotter gas that's moving some way. And if we then have a look in the infrared, so this is an image taken with the James Webb Space Telescope. You'll probably know this already, but the James Webb has hexagonal mirrors, and the hexagonal mirrors produce 6 spikes on the star. So we have to ignore the spikes, right? That's not real. We've got a 4-year-old at home, and he's just starting to draw things like this. And of course, everyone draws a star with spikes sticking out, right? But they're not real. I had to tell him, Felix, they're not real. The stars are just round. Yeah. So now...
Two gas jets.
That's it. We're seeing jets going in 2 different directions. The cloud is mostly transparent in the infrared, kind of like see a little bit of the billowy gas. So what we're seeing right in the middle here is a star in formation. This is what we call a protostar, and as the material is piling in, it's got a lot of excess energy. It goes into a big swirling disk, and the way that the disk works and the way the physics works is it has to expel some of that energy, and it does so through firing off these jets. The jets go in the north and south direction as the star is spinning, and then they slam into the material around it and they heat it up. So what we're seeing here is the heated up gas surrounding this star. Now, the reason I wanted to show this picture is because this is what our solar system would have looked like about 4.5 billion years ago. This is what we would have been. Your body, all the material that you're made from, and in fact this whole room and everything that we see around us was once like this. A big cloud of gas that was piling in, and then all the light material stays in the middle, that's the hydrogen, helium, and all the heavier material gets spun out, like a centrifuge really, and then that material is spinning around and coagulates and forms our planets. You know, so that's how a star in the solar system formed. So then all that hydrogen that's been floating around for 13.8 billion years, maybe it's been in previous generations of stars, it's certainly been in gas clouds floating around our Milky Way galaxy. It all gets pulled in through gravity, and it forms part of our solar system, and it formed our planet, and right now is forming your body.
Can I just ask?
Yeah.
You're differentiating the ejections there to be not jets, but actual dust more from a circular movement as opposed to a jet.
Ah, okay. So the disk of material which will eventually form the planet is right down in the middle here, about this size. But then the star is shooting out these jets which heat up the gas in the cloud and out. That's right, yeah. So the star is spinning like this with the big disk around it, and then the jets go up and down. Yeah, that's right, yeah. I don't think people quite understand how that physics works, but it seems to be a characteristic of new stars forming.
The only reason I mention it is because the dust, which obviously condensed eventually into a planetary system, so was more on an equatorial basis as opposed.
That's right. Yeah, that's right. Yeah, that's right.
You're saying that dust actually diffused round the whole globe of the star on an even basis.
It does. It starts off in a fairly even disk of dust and dust really, and then because it's going around very fast, it gets very hot. Friction heats it up, so you could basically see it as like molten. It's like liquid, and as the droplets touch, they grow and it builds up, and then another big droplet comes in and smashes it apart. So gradually the whole thing builds and builds and builds and then gets smashed apart and builds again until you get bigger and bigger, bigger structures which end up being planets. Yeah, yeah, yeah.
Is it possible to explain why only a few of the stars have got six
Oh, 6 spikes?
Yeah, whereas a lot of the other ones
Mm.
don't have any spikes.
Yeah, you're right. Okay. So here we've got here, this is the original image, and the James Webb is just overlaid. You can probably see there's an edge to it here. Yeah, that's where the edge of the James Webb image is. And then we're seeing the visible light image in the background. I've just overlaid one on top of the other. Do you see?
Right, but some of the dots don't have spikes at all, do they?
Yeah, that's right. So the visible image here, you can actually see it's got four. Some of the bright ones have four spikes, and it's to do with how the telescope is made and how the mirror is held by 4 struts in the
So it
middle.
has to have those spikes because of the hexagons.
Well, the James Webb is actually designed slightly differently to a normal telescope. The telescope that you might have and you use at home maybe it's a telescope which holds a mirror in with 4 struts, like it's got a secondary mirror. Right? The light comes in, hits the back mirror, comes into the secondary mirror, and that's held by 4 struts, which causes the diffraction spikes. We see 4 across like this. But the James Webb is made slightly differently, in that the actual mirror itself is hexagonal, and the detector is in a slightly different pace, but I mean, essentially that's what it's about. They're diffraction spikes.
Why does that have to create the spikes?
Yes, the way the light bounces around inside the telescope itself. It's one of those things that, for astronomy purposes, you can actually remove the spikes through some processing of the data, but actually for images like that, it's really difficult. So
it's built in hexagons because it's too big to build the other way.
yeah, that's right. So the James Webb Space Telescope has a 6.5 meter diameter mirror, which is basically from me to the size of this room. And in order to launch that up into space, they had to condense the mirror a bit and had it unfolding in a different way. And the hexagons is the best way. Yeah. A lot of modern telescopes are made with hexagonal pieces, right?
I've seen it,
Yeah. Yeah, so this is the beginning of our story in terms of our sun and our planets and the formation of our solar system, looking a little bit like this. Now, if we carry on a bit, oh yeah, here we go. Oh yeah, I've got it all here anyway, right? That's the idea there, the disk and the jets. And here's another example where we can see, we can't actually see the star, it's right hidden underneath. We get a disk of material and then these big jets coming off. Now, a little bit down the line, most stars form inside a big gas cloud with other stars in a cluster. So it's very likely that our sun would have formed with some brothers and sisters at the same time. And now, over time, that cluster disperses and all the stars just disappear. You know, can't tell which one's which anymore. But this here, anyone? Pleiades. It's Pleiades, exactly, yeah. So this is a cluster of stars, about 200 million years old.
Very young.
Which is pretty young, exactly, yeah, I know. 200 million years seems a long time, but actually in the scheme of things is a pretty young cluster of stars. And gradually these stars will disperse over time. And they're in the process right now of, in the middle of their lives, converting hydrogen to helium and making some of these other elements, small amounts of carbon and nitrogen, oxygen along the way, and using that in their process to create energy. So they're shining and making chemicals. Now, how do those chemicals end up in the next generation of stars? That's the next part of the puzzle. A planetary nebula, yeah. This is the Ring Nebula. This is an end stage of a star like our sun. So medium to small star, when it comes to the end of its life, what I mean by coming to the end of its life is it's running out of fuel. So it runs out of hydrogen, no more hydrogen left to convert to helium, so the energy source starts to fizzle out, and the star cools down and shrinks. And then it heats up and expands, and then it cools down and shrinks. So at the end of the life, the star goes unstable and pulsates. And each time it pulsates, it throws off a layer of material, of gas. And so what we're seeing here, there's somewhere in the middle here, there's a star that's fading out. And this is all the layers of gas that have been expelled over the last, let's say, 50, 100,000 years, something like that. And then it's being illuminated from the inside. Right? They are some of the most beautiful things to look at, planetary nebulae. Even with small telescopes, you can get something really quite spectacular. So this is a James Webb Space Telescope image you can see with the 6 points. You can always spot it, yeah? Now we're going to zoom out a little bit and include a slightly longer exposure image. And it gives you a bit more of a perspective, these beautiful layers and shells of material that have been expelled in previous times. Now, of course, remember this is a three-dimensional image, a three-dimensional object portrayed in 2 dimensions. So we have to think of this as more like a bubble rather than just a circle.
A flower.
It does, doesn't it? Yeah, there are petals. I totally agree. Yeah, isn't it beautiful? Yeah, and they're all the different colours. Whoever processed this image on the computer twiddled around the knobs and made it very beautiful, huh? Yeah. Now, to understand some of the physics, I've got a little video. Hopefully it'll work.
The nebula turns out to have a much more complex shape than we can see from Earth. The main structure of the nebula is a broad ring of nitrogen. That's the red ring you see. Hotter oxygen gas is seen here in green and fills the interior. What's even hotter still is helium, and it's seen here as blue oblong lobes perpendicular to the nebula's main structure. A number of dense, dark knots of gas circle the inside of the red nitrogen ring and have so far resisted the blast of stellar winds and radiation. The shadows of these knots can be seen as long, thin spikes around the ring. Glowing hydrogen also reveals the inner and outer halo lobes, which formed when the star began to burn out. This detailed three-dimensional model of the Ring Nebula will help astronomers understand the last stages of a star's life. Our Sun is expected to have a similar fate in about 5 billion years.
Astronomy is unusual. In fact, it is unique in being the only science where you can't do an experiment. So we can't go out there and twiddle and test things, or you can't make a star in the lab and try things out. It's in a sense passive. So we only just receive the information, and we have to be creative about what we do with that information and find different ways to find more information. So then these kind of models where you put it on the computer and turn it around and try a few things is essential to understand, how it's working.
With Sandage, you said once that astronomy is the only science where you can't actually touch what you study.
Yeah, right, exactly. Well, so it's quite, but we can here. We're made of the universe. I mean, you can't touch the stars, but we can touch and we can sense and feel and know the result of the stars in our universe, in our world, right? Yeah. So yeah, so I understand what he's getting at there. Yeah. So, let's just quickly recap there a bit. Yeah. So these planetary nebulae are how the material from a star like our Sun returns that stuff back into space for the next generation. When our Sun comes to the end of its life and becomes a planetary nebula, it will grow and will actually grow to the size of about Mars, is what we predict, and it will vaporize everything in that radius. So the Earth and everything on it will be vaporized in that process, and so all of the material from which we're made and our whole world is made will just return to space. It will then float off and become part of this stunning planetary nebula. And I can only hope that if there's any aliens looking at our solar system at that time, they will also go, wow, isn't that beautiful? Very possible that some previous generations of people lived on that star and are now a part of that that we're looking at. I mean, who knows, right? No, we don't know. Right. Stars form inside clusters. Some are small, like the Pleiades, and some are much, much bigger. So here's a very young cluster of stars inside a big cloud of gas, and the stars heat up the gas surrounding them and blow it up. And like a bubble expands, and the bubble's expanding, and then it starts to erode all the rest of the gas. Some of the gas is much denser and takes longer to erode. So we see these pillars. So we mentioned the pillars of creation. This is the so-called pillars of creation sticking up here. Yeah. So this is the Eagle Nebula. 7,000 light years away, which means light's been traveling to us for 7,000 years. It's in the Milky Way galaxy, not far away. Yeah.
Yet the light left before the Egyptians.
Exactly. Isn't that thing? Yeah. So the light left basically at the point of which we started to record history. Yeah. The whole length of our record history, that light's been traveling. Yeah. Yeah. The cluster makes stars of all different shapes and same shape, all different sizes, right? So some small, some big. This particular cluster has produced some very, very big stars, and those stars shine very brightly and use up their fuel very quickly, as we've said. So the energy that gets returned to space from these stars is what's really shaping all these knots and fingers. Now let's have a little look at this part here. This is one of, I think, the most spectacular images that James Webb has produced so far. It's the pillars of creation, but seen in infrared. So remember, infrared allows us to see a little bit further into the cloud. The clouds appear a little bit more transparent, opaque, translucent, sorry.
You're actually seeing stars form.
Exactly, exactly. So the effect of the hot material from the stars that are way up there that's slamming into these dense knots here is compressing the top surface, and so right up there on the tops of these little pillars there are new stars forming because the gas is getting compressed, and that's what causes the new burst of new stars. Yeah, you can see it here as well. Nice one here, and amazing wispy, actually this is very, very hot shock waves as they pass through the gas. And it's just like a sand dune and some wind, you know, how it erodes the shapes and the structures over time, produces something very beautiful. How does that happen? But actually, it's just the effect of the erosion of the gas. Yeah.
I was wondering how you're talking about it, next generation, but these are stars that have already been burnt out. So if the fuel's gone, how do they recreate something, but from something which is already burnt up?
Yeah. Okay. Okay. Yeah. So let's see. This is a cluster of stars which is about 3 million years old. So in that time, none of these stars which have just formed have come to the end of their life. They're all in the middle of their fast lane. Yeah, even the most massive stars which live very short lives are still going at this point. So we're not looking at any stars which have come to the end of their life here. And the effect of these stars are causing new stars to form in the tips of these little pillars here. So we're going to kind of ripple effect of new stars forming. And it won't be very long in a cluster like this, maybe another couple of million years, before one of these guys goes supernova, because they're massive and they live very short lives. Yeah, and that will completely disrupt everything going on here. The blast wave will blow all this stuff out, and we'll get lots, you know, the whole thing will be torn apart, basically.
It always amazes me that you don't actually see more supernova. You would have thought of all the, I'll say stars to simplify,
Yeah.
things that have been created, that there'd actually be more supernova, but we
Right.
don't see many of them at all.
Yeah, well, that's true, yeah. So our Milky Way galaxy, we've got about, what is it, about 100 billion stars, but we can only see maybe a quarter of them, because many of them are hidden behind layers and layers of gas and dust on the other side of the Milky Way. So it's very likely that if supernova happen around the Milky Way, we might not even know about them, we might not see them at all. Yeah, but plus on the other side, our lifetimes are very short compared to the timescales that are needed for a supernova to happen.
Compared with the amount of stars there are.
You might say, I hear what you're saying. Yeah, I hear what you're saying. Yeah, yeah,
There would
yeah.
be mathematics done already been done on them, wouldn't there?
Yeah, 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 that's right. So you can calculate the probability of a supernova happening that you can see. I mean, the last one I think that people recorded was in about 1600. And now we've identified which star it was that went supernova, and that's the Crab Nebula. And then I think there was one recorded by the Chinese, maybe 1100 or something like that. Maybe some other people know better than me. So there's been a few across recorded history, but
just outside the galaxy, wasn't there, in 87?
yes, that's right. So it's in the small Magellanic Cloud. That's right. Yeah. So that was the nearest one we could study very well. Yeah, you're right. Yeah.
Yeah, 1987.
1987. Yeah. So people did their best, but it was still the 80s. So yeah. The length of one of these pillars is about 1 light year.
About how?
About 1 light year. About 1 light year, yeah. So if we put that into context a little bit, so if we were to shrink the size of our sun to about a football or beach ball kind of size, about this size, then the next nearest star, our next nearest star is
4 or 4.25.
about 4.5 light years. Yeah, Proxima Centauri, yeah, exactly, about 4.5 light years. So on that scale, if the sun was the size of a beach ball, that nearest star would be Nairobi, Kenya.
Sure.
Yeah, about 7,000 kilometers away. Yeah, so, and that's 4.5 light years. So this distance here would be at a quarter of the distance from here to our next nearest star. The edge of the solar system, the whole solar system would probably be just in the tip there, all the way out to the Oort cloud. It's just the tiniest little part. So there's about 10 light hours to the edge of what we call our solar system, 10 light hours. And then you've got all that emptiness to the next star, and that's just the next star. So it gives you a sort of feeling of, you know, maybe if our solar system was up here, the next nearest star to us would be down here somewhere. Yeah. There's lots of examples of this kind of thing. Very young stars here, and big clouds of gas from which they have formed and are now blowing away. This is a nice example. This is a star that's been forming inside the cloud and is actually making its own bubble now inside. And this star here is the biggest star that we've ever known, ever detected, ever measured. It's about 120 times the size of our sun, and that scale would live only about 2 million years. It's like fast lane, burn bright, burn hot, let's go for it kind of thing, yeah? And then it'll go boom, and the whole thing will be, yeah, disrupted, yeah.
So which one was that?
Yeah, so in here.
That one, yeah.
Yeah, it's actually part of, well, I mean, it's a part of a binary system, but it seems improbable how massive it is, but then...
Is that because if it's any bigger, it turn into a black hole?
Well, it's very likely that a star that size, when it comes to the end of its life, so this is a good transition actually to the next part, right? So we're thinking about stars that are maybe 8 to 10 times the size of our sun or bigger. When they come to the end of Earth, they won't just contract and cool and expand and control and fizzle out. Actually, they contract, and the amount of gravity pulls it in so much that it goes in and reaches a point where the material can no longer be squeezed anymore. There's a limit to the amount of material that you can squeeze into one place. So it hits basically a brick wall at that point and then explodes. So that is a supernova. The star can no longer hold itself up. It contracts and explodes. Now, even more massive stars, like let's say this guy, it gets to that point where it hits the brick wall. Physics says it cannot carry on contracting anymore, and then something else happens and it implodes into a black hole. Now, we don't understand how that physics works, but that's what happens. So the star itself implodes to a single point, a single point we call a singularity, where the entire mass of the star ends up being a single point. Physics, we'd have no maths for that, basically.
So do you think there's a limit on the size of a star, or is that the last?
Yeah, there is. It does seem to be about 120 to 150 times the mass of our sun is about how big it. So it's the time for material to keep piling in, and then the star switching on and pushing it away.
So something must happen to ones that try to be bigger, right?
Yeah.
Which is maybe black hole.
Well, I think what happens is that if they're trying to get bigger, the star itself will actually start blowing the material out. Right? It can't pile in fast enough, you know. So the black hole happens at the end of its life when it explodes. Yeah.
I've often wondered what a singularity involves. It can't be material as we understand it. It must be converting it all back into energy.
Must be. Yeah, must be. Yeah. It becomes pure energy again. I mean, you can only guess. We know the effect of a black hole, and we know how the event horizon works, and we can calculate the mass of a black hole, but we just don't know what's going on inside it. Yeah.
You want to get your lecture down with questions. If that goes into the singularity of the black hole, does that lend itself to a multi-universe?
Ah.
Are you coming on to that?
No, I'm not going to come on to that. So I'm going to say that's beyond the scope of this talk. I'll just take that talk, take that question. But yeah, I mean, you know, it could do. There are lots of theories about that. Yeah. Now, what happens if you go into a black hole? It might be a wormhole to another universe. I mean, who knows?
Well, I wasn't going to say that, but I mean, on the basic physical description that you're going through, about that will end up as a singularity.
Yeah.
And ends up to the black hole. Of course, it could be that our universe, which starts out as we know it, 13.8, was a singularity. It could have been actually because of a previous black hole.
It's a serious thought. It's a serious thought. Yeah. Exactly. Yeah. Our universe, the Big Bang itself may have been the start of a black hole. Exactly. I know it's a serious thought, but the question is, how can you test it? So far, no one has. There's all sorts of theories about what's saying. No one's come up with something you can actually test and make measurements and confirm. So that's where we're at with those kinds of theories. Yeah. Now, the last thing I wanted to bring into our talk today is here. Any ideas? What is this?
Vortex of gases.
A vortex of gases?
And dust.
Mm-hmm.
Interstellar medium.
It is part of the interstellar medium, yeah. So it's part of the stuff in between stars.
Dust.
There's very likely dust incorporated in there, but this actually isn't an image of the dust. So you may recognize it when I just show you it's part of a much bigger area. This is the Veil Nebula.
Yeah.
And it's the most incredible thing to be able to see that, isn't it? So, isn't that tiny part? Yeah. So up here we have the Witch's Broom Nebula up in this part here, which is part of this much bigger Veil Nebula. So the Veil Nebula, this is a supernova remnant. So this is the aftermath of an explosion of a supernova. The supernova is long faded somewhere in the middle there, but the hot explosion is slamming into all of the gas around and causing it to heat up, and we're seeing here very hot gas. Now this is a visible light image, but the hot gas itself that's filling the interior is invisible in the visible. It's not visible. But you can see it in X-rays. So if you take an X-ray image of this, I've got a few things. Yeah, there we go. X-ray image of this area here. You can then measure the amount of light that comes from different chemicals in this explosion. So with spectroscopy, you know, you can kind of narrow down on the light that comes from sulfur or from carbon, calcium, that kind of thing. So you can take an image of this here in sulfur silicon, calcium, iron, and put it all together. And when you've got that kind of image, you can then guesstimate how much material has been produced of these different elements. And it turns out that of sulfur, for example, there's about 50,000 times the mass of our planet in sulfur, just from one explosion. Iron is about 100,000 times the mass of our planet in iron, just from one explosion. And of course it gets blasted out into space and floats around, and then it gets incorporated into new clouds, and eventually it got incorporated into our solar system and into our planet. And now we have, I don't know, sodium chloride, salt, or aluminium metal. We have magnesium in our bodies. We have, you know, always the calcium makes teeth and bones, all that kind of stuff. And all these chemicals that you are made of, you essential to your life, come from here, come from a supernova explosion.
I was going to say, for a fairly modest piece of equipment, you can put on your phone a picture of the nebula.
Oh,
Anybody can do it.
wow, wow. That's another thing. And that's literally been the last 2 years probably, isn't it?
You know
Yeah.
all about that, don't you?
Okay, so we now got a little bit more of a view of our story, right? So we started off with just hydrogen, and we get a star which converts hydrogen into helium, producing light, but also produces a few of the little lighter elements. And then small stars come to the end of a life planetary nebula, and it diffuses back slowly. And bigger stars have a supernova explosion, and in the explosion have enough energy to produce some of these heavier ones. So we've talked copper here, iron, magnesium, yeah, calcium, magnesium, yeah, all those other ones, yeah, yeah, sodium, come from supernovae. How are we doing time-wise? Yeah, the what? Yeah, yeah. So have we got a moment? How close are we to the end? Yeah, yeah. Yeah, I think we started a little after past, but sure. If you don't mind, one little, yeah. So the one I just highlighted here, this is gold, and we don't need gold to live. So the body doesn't need gold, and the reason why is that gold is inert in the body, doesn't do anything. Yeah, and that's why we use it for we used it for fillings, in filling teeth, because it's entirely inert, doesn't do anything. And we have, anyone's got gold jewellery, most people have got some kind of gold somewhere, or have had it sometime in the past or whatever. A lot of people, the gold will gradually and very slowly diffuse into the body, and we get just, you know, a few atoms of gold sitting in our body, not doing anything. But of course, gold is very, very precious, and we see it as being rare and precious. But actually in the universe, it's extraordinarily rare, because gold cannot be made by a supernova. Supernova doesn't have enough energy to squeeze together the elements to create something as heavy as this. This has a lot of protons and electrons here. So we have to turn to some even more crazy stuff. This is a galaxy where we identified what people call a kilonova. A kilonova is the next step up. Supernova, astronomers love the superlative, so we get one step up. It's a kilonova, and it is very likely to be, this one here, the crashing together of two neutron stars. When a star goes supernova, it contracts until it hits that brick wall, and it can't contract anymore. The material within that brick wall turns all to neutrons. So we have the remnant of that is entirely a ball of neutrons, very, very compressed and dense. So let's say we've now got two neutron stars in orbit around each other, and they're spiraling inwards. At some point, the neutron stars will collide, and at that point, physics cannot tell us what happens. We still don't understand, but an extraordinary explosion happens. And in that moment, we have enough energy to create some of the heavy elements. Yeah.
Is that detectable by is it LIGO?
That's right. Yeah, that's right.
Is that how they know about it?
That's right. Yes, that's right.
And is that very sudden one, like it is with the black holes?
Yeah, so I think
They must be so going so quickly. That's why it's so sudden.
That's right. You're exactly right. So the collision of neutron stars and the collision of black holes, merging black holes, produces such an incredible explosion. It actually creates ripples in space-time, which we can detect with these recent experiments.
Objects, are they much more rare than black holes?
Very.
The fact that the two of them are colliding rather than one black
Yeah.
hole and one of those.
So a neutron star is the product of a supernova of stars that are medium to big. A black hole is the product of a very, very big star. So these are more common. A neutron star, black holes are less common. Yeah, that's right. Yeah. So the fact that we have gold, enough gold to make all of our jewellery and everything like that, and fillings and things, is the result of these incredibly rare explosions having happened over the history of our universe. So I think that kind of finishes off our story a bit, at least the story of how the elements were created that make up our world, that make up our life, and how we can live. Yeah. Yeah.
What about the heavier elements, though? Because if we've only got to gold,
Yeah.
it's almost impossible to produce
Yeah.
things that happen in the universe.
Some of these things can only be produced in the lab. They don't occur naturally. Some of these really heavy ones up here. Yeah. And also, it's not quite so. Neutron star explosion. Although we don't really understand the physics fully, but it seems like it can produce. It's not just gold. It's just I highlighted gold because that's interesting to us. But yeah, so mercury and lead and things. They all come from those kind of things as well. Yeah. Yeah.
How did the gold get here?
Yeah. Yeah.
How did it get here?
I know, isn't it? Yeah. So the explosion, it all just floats, vaporized, all gas floating in space, and then it just gets swept up into a new cloud, and that cloud eventually starts to coalesce, and then a little star forms in the middle, incorporating the material from the previous generation. Yeah. So we get this long generations of stars that have to have lived to create everything that we need.
And then we have to mine it to get it out
Yeah.
of the earth.
Yeah, that's right. Yeah.
It's formed as part of the formation.
That's right. Yeah, it's all mixed up in the material that our planet's made from. Yeah.
The gold is in the form of gas.
It was. In space it was, and then it solidified into our planet, and then it became solid.
But what I mean is, when you said it was a cloud of gas,
Yeah.
the gold was in the form of gas.
That's right. Yeah. Yeah.
So it can be,
Yeah.
what's it called it?
Vaporized.
Vaporized.
Vaporized. Yeah. It was all vapor. Exactly. Yeah. 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 Yeah.
Which element is the heaviest to be produced naturally like that?
That's a good question. I don't quite know. What's the heaviest element that naturally? I don't know the answer. I don't know. Yeah.
It's actually uranium.
Uranium's the heaviest. Yeah. So that's up here somewhere, isn't it?
It's just a set of numbers.
To be done.
You've taken them out, you've got 98.
Yeah, so
Oh, it's down there.
Down there. Yeah. Uranium. Yeah. 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 So thanks for staying awake. No, that's it. I'll come to the end now. Thank you very much. Yeah. 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 Thanks.